the planetary physics paradox. What if the most realistic target for humanity's second home isn't a planet that welcomes life, but simply the world that tries the least aggressively to kill us? Imagine standing on a surface where stepping outside without a suit means your blood literally boils in under 15 seconds, where the soil beneath your boots is saturated with rocket fuel toxins, the air is a suffocating cloud of carbon dioxide, and an invisible rain of cosmic radiation quietly snaps your DNA with every second that passes. This isn't a sci-fi horror planet on the outer edge of the galaxy. This is Mars. And yet, when space engineers calculate the brutal physics of energy, mass, and raw chemistry across our entire solar system, they land on a mind-bending paradox. Mars is an absolute environmental nightmare. But it is also the only world in the entire known universe where the laws of physics don't completely close the door on a self-sustaining human civilization. To understand why, you have to look at the alternatives, not as a casual tour of the solar system, but as an engineering failure analysis. Take the Moon, for example. The Moon is right on our doorstep, barely 3 days away, making emergency resupply or evacuation realistic. But the Moon carries a fatal structural flaw: its rotation. A single lunar day lasts nearly 29 Earth days. That means any lunar base faces 2 continuous weeks of scorching, uninterrupted sunlight, followed immediately by 2 continuous weeks of pitch-black, deep-freeze night, where temperatures plunge to minus 130 degrees Celsius. During the Apollo missions, NASA intentionally landed during the early lunar morning to avoid these extreme thermal swings. Surviving a 2-week lunar night requires massive battery arrays or continuous nuclear power just to prevent life support systems and structural joints from freezing and fracturing. Furthermore, lunar dust is made of razor-sharp glass shards created by billions of years of meteorite impacts without an atmosphere to weather them. During Apollo 17, astronaut Harrison Schmitt reported that lunar dust destroyed suit vacuum seals, jammed mechanical visors, and triggered severe respiratory reactions inside the lander within hours. Then look at Venus. On paper, Venus is Earth's twin, sharing almost identical mass and surface gravity. Some mission planners have suggested floating cloud habitats high in the Venusian atmosphere, where temperatures and pressures mirror Earth. But a floating city carries a terrifying structural trade-off. It has no ground underneath it. Every single gram of iron, silicon, titanium, and heavy machinery needed to build, repair, and maintain that city would have to be lifted mid-air or continually shipped across space. On the surface below, atmospheric pressure equals being 1 kilometer underwater, and 460-degree heat melted the Soviet Venera 13 probe in just 2 hours. You cannot mine a world where your tools melt before they touch the dirt. This leaves us with Mars. And the moment you dissect Mars, the true engineering trade-offs reveal themselves. Start with the day-night cycle. A Martian day. A sol lasts 24 hours, 39 minutes, and 35 seconds. This isn't just a convenient number, it solves a deep biological problem. Human circadian rhythms are hardwired into a cluster of nerve cells in the brain that regulate our internal clock. Earth-based isolation studies show human biology can naturally adjust to a 39-minute daily shift. Mars allows settlers to maintain natural sleep-wake cycles without the severe biological decay caused by the Moon's 2-week night. Then look at gravity. Mars operates at roughly 38% of Earth's gravity. On Earth, a modern spacesuit feels heavy and restrictive. On Mars, its felt weight drops by more than half. This gravity well sits in a precise sweet spot, strong enough for fluid dynamics to work in plumbing and life support loops, strong enough to keep concrete anchored, and strong enough for humans to walk naturally. Yet, this lower gravity creates a double-edged sword. Escaping Earth's deep gravity well requires immense velocity. Escaping Mars requires less than half that speed. That mathematical difference drastically reduces the fuel payload needed for return rockets, making two-way interplanetary transit physically possible. The trade-off, however, is human biology. We know from decades of space station data that weightlessness causes humans to lose bone mineral density every month, alongside heart shrinking and muscle atrophy. What science doesn't yet know, because no human has spent extended time in partial gravity, is whether 38G is enough to stop this physiological decay, or if Martian settlers will suffer slow, irreversible skeletal degradation over decades. The decision to build on Mars ultimately comes down to a single engineering discipline: in situ resource utilization, or living off the land. A colony that relies on continuous supply crates from Earth is not a colony. It is an offshore base waiting for a budget cut to kill it. Every launch from Earth is bound by Tsiolkovsky's rocket equation. The math proves that to carry more mass into space, you need exponentially more propellant, which adds more mass, requiring even more propellant. To break out of this exponential penalty, a starship must land on Mars, refuel using local planetary resources, and fly home. Mars is the only world in the inner solar system that provides the exact chemical inventory to make this work. Its atmosphere is 95% carbon dioxide. Beneath its red surface regolith lie vast sheets of subterranean water ice, stretching across the mid-latitudes, a fact confirmed directly by NASA's Phoenix lander when its robotic arms scraped away topsoil to reveal pure water ice that sublimated over the following days. When you have carbon dioxide and water, you have the fundamental building blocks of modern rocketry. By running electricity through water, you split it into hydrogen and oxygen. You then combine that hydrogen with atmospheric carbon dioxide in a high-temperature reactor over a nickel catalyst, a process known as the Sabatier reaction. This yields pure methane and water. The methane is liquefied, and the oxygen is cryogenically cooled into liquid oxygen. This exact chemical combination drives modern rocket engines, like SpaceX's Raptor. Mars is not just a destination. It is a planetary-scale propellant factory sitting in deep space. But solving the fuel problem immediately exposes the next, far more dangerous set of engineering trade-offs: the planetary environment itself. Mars lost its global magnetic field billions of years ago as its molten core cooled and solidified, shutting down its internal dynamo. Without a magnetosphere, the solar wind stripped away most of the atmosphere, leaving the surface exposed to a continuous shower of galactic cosmic rays and solar particle events. On Earth, our atmosphere and magnetic field provide an ironclad shield equivalent to living under a 10-meter-thick layer of water. On Mars, an astronaut standing on the surface absorbs a daily radiation dose significantly higher than the Earth average. High-energy atomic particles pass directly through human tissue, snapping DNA strands and elevating lifetime cancer risks. Physical shielding solves this, but at the cost of immense mass. To lower radiation exposure to safe levels, a Martian habitat must be buried under 2 to 3 meters of packed dirt, or built inside ancient underground lava tubes left behind by extinct volcanoes. The moment you move to Mars, you accept that human life must adapt to living subterranean. The soil itself introduces another hidden failure mode. Analysis from NASA's Curiosity and Perseverance rovers revealed that Martian soil contains toxic perchlorate salts. On Earth, perchlorates are used in rocket propellants and industrial explosives. On Mars, they sit in the dirt you step on. Perchlorates are powerful thyroid disruptors in humans and toxic to most plant life. If astronauts track Martian dust inside the habitat on their boots or suits, that dust dries, becomes airborne inside the life support system, and slowly poisons the crew over months of inhalation. Every airlock design must therefore incorporate automated suit wash bays, magnetic dust extractors, and negative pressure isolation zones just to keep the dirt outside where it belongs. Even the air presents a mechanical trap. Atmospheric pressure on Mars averages less than 1% of Earth's sea level pressure. This sits well below the biological threshold where the boiling point of water drops to human body temperature. Without a pressurized suit or habitat, the moisture in your lungs and eyes would instantly vaporize, causing rapid loss of consciousness. Because internal pressure inside a Martian habitat must be kept near normal Earth levels so humans can breathe, the structural walls face a continuous outward pushing force of roughly 10 tons per square meter. A Martian dome isn't holding the weight of the roof up like a building on Earth. It is acting like a giant pressure vessel, stopping itself from exploding outward into a vacuum. Every door, airlock seal, and window joint is under continuous mechanical tension for decades. And so, the true picture of Mars emerges. It is not a planet chosen because it is welcoming, easy, or beautiful. It is chosen because it sits precisely on the razor-thin line of what human engineering can overcome. It is a world where the water is locked in the dirt, the air is poison, the surface is irradiated, and the pressure is a vacuum. But it is also a world where the daily clock matches our biology, the gravity is manageable, and the raw elements to rebuild an entire industrial civilization are waiting right beneath the dust. Mars is a mechanical puzzle bound by unforgiving laws of physics, and the very first piece of that puzzle isn't building a base on the red soil. It is surviving the 6 months of absolute nothingness required just to reach it, the 6-month void. What if the most dangerous part of building a home on Mars isn't living on the planet itself, but surviving the 6 months of absolute nothingness required to reach it? When people picture a human mission to Mars, they imagine the heroic moments, the fiery launch from Earth, the red dust swirling around boots, or the first flag planted in the regolith. But space engineers know that the most unforgiving test of human survival happens in the quiet, empty dark between worlds. A spacecraft bound for Mars isn't just a vehicle traveling from point A to point B. It is an isolated, closed-loop machine drifting through a deep space environment that actively strips away its power, degrades its metals, and attacks the biological integrity of its crew. The first fundamental problem of interplanetary travel is celestial mechanics. You cannot simply point a rocket at Mars and ignite the engines. Both Earth and Mars are moving in elliptical orbits around the Sun at different speeds. Earth orbits the Sun at nearly 30 kilometers per second, while Mars, farther out, moves at roughly 24 kilometers per second. Because of these orbital mechanics, Earth and Mars align in an optimal position only once every 26 months. This window, known as an orbital conjunction, dictates the entire timeline of human spaceflight. Missing this window means waiting another 2 years on Earth before the geometry allows for another attempt. To cross the void between these two moving targets using the minimum amount of rocket fuel, engineers rely on a Hohmann transfer orbit. Instead of flying in a straight line, the spacecraft executes a precise engine burn to break out of Earth's gravity. Entering an elliptical orbit around the Sun that gradually sweeps outward until it intersects with the orbit of Mars 6 to 8 months later. This brings us to the first brutal engineering trade-off: speed versus mass. If you want to shorten the transit time to 3 months to protect the crew from long-term space hazards, you must burn significantly more propellant. But carrying that extra propellant increases the overall mass of the ship, which requires an exponentially larger rocket to launch it from Earth in the first place. A compounding mathematical trap driven by the rocket equation. As a result, mission planners are forced to accept a long, slow, 6-month cruise. And during those 6 months, the spacecraft becomes a floating island exposed to the raw physics of deep space. The primary invisible killer during this transit is galactic cosmic radiation. While astronauts aboard the International Space Station are partially shielded by Earth's magnetosphere, a spacecraft in deep space has no planetary shield. Cosmic rays, high-energy atomic nuclei, accelerated to near-light speeds by distant exploding stars, pass effortlessly through traditional aluminum rocket hulls. When a cosmic ray collides with the heavy metal atoms of a spacecraft's structure, it shatters those atoms in a violent nuclear collision. This process creates a secondary spray of high-speed neutrons and subatomic fragments, a phenomenon known as secondary radiation shower. In a cruel twist of physics, an inadequately shielded metal hull can actually generate more dangerous radiation inside the living quarters than if the ship had no heavy metal walls at all. Real space missions have already measured this hazard directly. In 2012, NASA's Curiosity rover made its 8-month journey to Mars, tucked safely inside its cruise stage. On board was an instrument called the Radiation Assessment Detector, which measured every high-energy particle striking the spacecraft throughout the transit. The data revealed that during a standard 6-month cruise, an astronaut would absorb a radiation dose roughly equivalent to receiving a full-body CT scan every 5 or 6 days. To mitigate this without adding thousands of tons of useless lead shielding, spacecraft engineers turned to hydrogen-rich materials. Hydrogen atoms are nearly identical in mass to incoming high-energy protons, making them far more effective at absorbing kinetic impact without producing secondary radiation showers. This is why modern long-duration ship designs place the crew's living quarters directly inside the center of the spacecraft, surrounded entirely by the ship's liquid water reserves and plastic polyethylene fuel tanks. The crew literally sleeps inside a liquid shield. Yet, while radiation attacks the cells from the outside, the microgravity environment of deep space quietly dismantles the human body from within. Without gravity pulling fluids toward the feet, fluids inside the human body redistribute toward the head. Blood pressure in the upper body rises, causing the heart to shrink over time because it no longer has to work against gravity to pump blood. Bone tissue, sensing no physical load, begins to reabsorb calcium into the bloodstream at a rate of over 1% per month. During long stays on the Russian space station, Mir, and later the International Space Station, astronauts experienced severe physiological decay despite spending 2 hours every day using heavy resistance exercise equipment. Upon returning to Earth's gravity, many could not stand unassisted for days. Now imagine an astronaut crew undergoing that same biological degradation across a 6-month deep space transit, only to arrive on Mars, where they must immediately perform high-stress physical landing operations without a medical team waiting to assist them. Engineers have proposed tethered artificial gravity systems, where the spacecraft connects to an expended rocket stage via a long cable and spins around a central axis. This rotation generates centrifugal force, mimicking gravity along the outer hull. But spinning a spacecraft introduces complex mechanical hazards. The rotating joint mechanisms represent massive single-point failure risks, and any slight shift in fuel or cargo weight inside the ship can destabilize the spin, tumbling the vessel wildly out of control. While engineers wrestle with biological survival, the spacecraft's mechanical systems face their own silent decay. Propellant boil-off. To fire the engines needed to slow down when arriving at Mars, the ship must carry cryogenic propellants, liquid methane and liquid oxygen, stored at temperatures near -180 degrees Celsius. In the vacuum of space, heat from the distant sun continuously radiates onto the ship's hull. Even with advanced multi-layer reflective insulation, small amounts of thermal energy bleed into the propellant tanks. When cryogenic liquid warms up, it boils into gas, causing pressure to build inside the tank. To prevent a catastrophic explosion, that gas must be vented out into space. Over a 6-month voyage, venting boiled-off gas means losing precious fuel needed for the landing burn. To solve this, NASA and private aerospace teams have developed active cryocoolers, essentially industrial-grade space refrigerators that constantly pump heat out of the fuel tanks. But active cooling demands continuous electrical power, which in turn relies on massive solar arrays or nuclear reactors that bring their own mechanical failure risks over months of uninterrupted operation. If a single coolant pump fails 3 months into the transit, the propellant slowly begins to boil away. By the time the ship reaches Mars, it may no longer carry enough fuel to slow itself down, transforming a multi-billion-dollar human mission into a silent ghost ship sailing past its target into the deep outer solar system forever. Every system aboard an interplanetary transit vessel exists in a state of delicate, high-stakes balance. The structural mass, the radiation shielding, the life support loops, and the fuel management systems are tied together in a chain where the failure of one link cascades into the rest. If the crew survives the radiation, avoids irreversible bone loss, and keeps the fuel cold through 6 months of silent drifting, they earn only one reward: the right to fall toward Mars at 20,000 kilometers per hour. And as the red planet fills the viewport, the spacecraft must transition from a quiet floating habitat into a violent battering ram, diving directly into the thin Martian atmosphere for 7 minutes, where there is zero margin for error, zero chance of aborting, and no second chance. Landing on the red planet. What if the most dangerous hurdle in human history isn't crossing 100 million kilometers of open space, but surviving the final 7 minutes required to touch the ground? Aerospace engineers call this phase entry, descent, and landing, or simply the 7 minutes of terror. When a starship approaches Mars, it isn't gliding gracefully toward a runway. It is plummeting toward a planet at roughly 20,000 kilometers per hour. At that speed, the difference between a historical human milestone and a crater on the Martian surface comes down to an unforgiving sequence of automated decisions where a single sensor delay or mechanical stutter means instant destruction. The core engineering paradox of landing on Mars lies in its atmosphere. If you want to land a spacecraft on Earth, you have a thick atmosphere to do almost all the heavy lifting. Heat shields burn off the excess velocity, and massive parachutes slow the lander down to a gentle touchdown. If you want to land on the Moon, there is zero atmosphere, meaning you rely entirely on precision rocket engines from start to finish. Mars sits in a cruel, frustrating middle ground. Its atmosphere is thick enough to generate extreme friction, reaching thermal temperatures over 1,500 degrees Celsius that can instantly melt structural aluminum. Yet, that same atmosphere is less than 1% as dense as Earth's, making it far too thin to slow down a heavy human landing craft using parachutes alone. When NASA landed the Curiosity and Perseverance rovers, each weighing roughly 1 ton, they pushed parachute and skycrane technology to its absolute physical limit. A human-class lander, carrying crew, life support hardware, and heavy return propellant, will weigh upwards of 100 tons. A parachute large enough to slow down a 100-ton starship would have to be the size of a city, and the fabric would tear itself to pieces under the dynamic pressure long before it could deploy. This forces engineers into a radical structural trade-off: supersonic retropropulsion. As the spacecraft plunges into the upper atmosphere, it must orient its heat shield forward, using atmospheric drag to bleed off roughly 90% of its kinetic energy. The air in front of the heat shield compresses so rapidly that it turns into a blowing wall of ionized plasma, blinding the ship's communications and leaving the crew in total radio blackout. During these critical minutes, the ship is flying completely blind from Earth. Because radio signals take up to 20 minutes to travel between Earth and Mars, human mission controllers cannot manually steer or correct the lander. The spacecraft's onboard guidance computers must continuously calculate air density, wind shear, and structural stress in real time, executing every maneuver autonomously. Once the heat shield slows the ship down to supersonic speeds, still moving faster than a rifle bullet, the lander faces a terrifying transition. It must flip its massive hull around mid-air and ignite its main rocket engines directly into the oncoming supersonic airflow. This maneuver, known as a landing flip, has never been attempted with a heavy human payload on another planet. Firing rocket engines into an opposing supersonic airstream creates extreme acoustic shock waves and aerodynamic turbulence. If the engine thrust is slightly uneven, or if the atmospheric turbulence tilts the ship beyond its center of mass, the spacecraft will tumble violently and break apart under structural aerodynamic loads. Real-world testing on Earth has already proven how tight this margin of error actually is. During early prototype tests of heavy, reusable landers, subtle pressure fluctuations in the engine fuel lines or tiny delays in vectoring control thrusters led to explosive structural failures in the final seconds before touchdown. On Mars, where there is no atmospheric oxygen, those engines must ignite instantly using stored cryogenic liquid methane and liquid oxygen, leaving zero allowance for a failed reignition. If the engines ignite successfully, another silent threat emerges from the ground itself: regolith erosion. In the final 50 meters of descent, the immense thrust from high-power rocket engines slams directly into the dry Martian topsoil. The superheated rocket exhaust carves deep craters into the landing site, blasting fine, sharp regolith particles outward at hypersonic speeds. This sandblasting effect creates a double failure mode. First, the flying debris can puncture landing gear, scour external sensors, or damage delicate heat shield tiles needed for the journey home. Second, as the high-velocity gas excavates the ground directly beneath the lander, it creates a blinding dust plume, a total visual blackout, while unpredictably shifting the stability of the soil. If the engines carve an uneven trench underneath one side of the ship, the lander can tilt over upon contact, tipping a multi-story structure onto its side in a catastrophic crash. To prevent this terrain destruction, landing site selection relies on high-resolution orbital reconnaissance from spacecraft like NASA's Mars Reconnaissance Orbiter. Engineers look for ancient, flat, basaltic plains like Utopia, Planitia, or Olympus Mons runoff basins, where underlying bedrock can support the immense weight of the ship without collapsing. If the guidance computer successfully navigates the atmospheric entry, executes the supersonic flip, survives the shock waves, and settles the ship onto stable bedrock, the engines finally go quiet. Inside the habitat, the violent vibrations, thermal roaring, and G-forces vanish, replaced by an eerie, heavy silence. For the first time in 6 months, the crew is no longer weightless. They are pressed into their seats by the steady, unyielding pull of 38% Martian gravity. Through the viewport, the glowing plasma of entry has cleared, revealing a cold, rust-red horizon under a pale butterscotch sky. The 7 minutes of terror are over. But as the landing systems power down and the heat shield begins to cool in the -60-degree air, the crew realizes a sobering truth. Surviving the crash landing was simply the admission price. Out there, beyond the dual-sealed airlock hatches, sits a barren world with no oxygen to breathe, no liquid water on the surface, and a toxic soil waiting to be tracked inside. The void of space has been replaced by the quiet, frozen reality of Mars. and the clock on their finite life. Support tanks is already ticking. Building the first base. What if the greatest architectural challenge in human history isn't building a structure that can hold its own weight up, but building a structure that can stop itself from exploding outward while keeping a silent, lethal environment from creeping in? When people imagine the first human habitat on Mars, they picture shiny glass domes gleaming under the sun, looking out over the red horizon. But architectural engineers know that a glass dome on Mars is a death trap. To build a habitat that survives for decades on another world, you must abandon every traditional rule of Earth-based construction and design. A structure that can withstand severe mechanical tension, continuous atomic-level radiation, and violent thermal swings, all without a single supply truck coming from Earth to deliver replacement steel or concrete. The first fundamental problem of Martian architecture is atmospheric pressure differential. On Earth, a building's primary job is to fight gravity, to support the heavy downward weight of its roof, floors, and occupants against the ground. On Mars, where atmospheric pressure is less than 1% of Earth's sea level baseline, the internal physics flip completely. To keep human beings alive without pressure suits, the interior of a Martian habitat must be pressurized to roughly 1 bar, or about 101 kilopascals, with a breathable mix of nitrogen and oxygen. This creates a massive pressure difference between the inside of the base and the thin void outside. Every square meter of internal habitat wall faces an outward pushing force of roughly 10 tons. A Martian habitat is not a house, it is a giant, high-pressure vessel sitting in a vacuum. Every structural seam, airlock gasket, and window frame is under continuous, relentless mechanical stress, trying to tear itself apart from the inside out. If a single structural joint suffers material fatigue and cracks, the result isn't a simple draft of cold air. It is an explosive decompression, where pressurized atmosphere bursts outward, ripping structural panels apart and leaving the interior exposed to the freezing vacuum within seconds. This mechanical tension is compounded by extreme thermal stress. Because Mars has a thin atmosphere that cannot hold on to heat, the surface experiences violent daily temperature swings. Near the equator, a pleasant summer afternoon might reach a high of 20 degrees Celsius. But as the sun sets, that heat radiates instantly into space, plunging temperatures down to -80 or even -100 degrees Celsius before dawn. This rapid, 120-degree daily temperature swing causes structural metals and polymers to continuously expand and contract. Over months and years, this constant expansion and contraction creates microscopic stress fractures along welds and joints. A quiet, invisible process known as thermal fatigue. A joint that holds pressure perfectly during month, one can suddenly snap under thermal fatigue in year 3, proving that surface structures face a hard physical limit on their operational lifespan. Yet, thermal stress and pressure differentials are only the visible hazards. The far more insidiously destructive force comes from above: galactic cosmic radiation and solar particle events. Earth's massive liquid iron core generates a magnetic field that acts as a global shield, deflecting harmful cosmic particles around the planet. Mars lost its global magnetic field billions of years ago when its core cooled. As a result, deep space radiation rains down on the Martian surface uninterrupted. High-energy protons and atomic nuclei pass directly through standard aluminum or composite habitat walls, breaking chemical bonds, degrading structural polymers, and exposing human inhabitants to dangerous daily radiation doses that drastically elevate lifetime cancer risks. To protect the crew, a habitat must carry massive structural shielding. Engineers calculate that to bring radiation exposure down to safe, Earth-equivalent levels, a habitat must be encased under a protective shield, equivalent to 2 to 3 meters of packed Martian dirt, or roughly 1 meter of solid water ice. This brings us to the core engineering trade-off: deployable mass versus local construction. If you attempt to bring heavy steel shields and radiation bolts from Earth, the rocket mass becomes impossibly high. But if you rely entirely on local Martian material, you must carry heavy robotic excavation machinery that can survive the abrasive dust and operate autonomously in freezing temperatures before the humans even arrive. To solve this, mission planners have turned away from surface domes and embraced a subterranean strategy: natural lava tubes. Billions of years ago, when Mars was volcanically active, massive rivers of liquid basaltic lava flowed across its plains. As the outer crust of these lava rivers cooled and hardened in the freezing air, it formed solid rock roofs. Eventually, the liquid lava inside drained away, leaving behind vast hollow underground tunnels known as lava tubes. Orbital imagery from spacecraft like NASA's Mars Reconnaissance Orbiter has revealed hundreds of skylights, collapsed holes in the surface terrain that lead directly into these ancient subterranean caverns. Lava tubes represent the ultimate natural shelter on Mars. Their solid basaltic rock roofs, often 10 to 20 meters thick, provide instant, total protection against galactic cosmic radiation, micrometeoroid impacts, and violent surface dust storms. Furthermore, inside a lava tube, the wild daily temperature swings of the surface disappear entirely. Deep underground, the ambient temperature remains locked at a stable, continuous -60 degrees Celsius day and night. While still freezing, this thermal stability eliminates the destructive daily thermal expansion and contraction that destroys surface structures. The operational plan for building the first base involves a hybrid construction architecture, inflatable habitats deployed inside these subterranean caverns. Instead of shipping heavy, rigid metal walls from Earth, landers deploy compact, multi-layered inflatable modules built from high-strength synthetic aramid fibers like Kevlar and Vectron. These fabrics possess a tensile strength significantly higher than steel at a fraction of the mass. Once positioned inside a lava tube by autonomous rovers, the inflatable modules are pressurized, expanding into large, multi-story living and working quarters. The multi-layered wall of an inflatable habitat is a masterpiece of materials engineering. The innermost layer consists of an airtight bladder made of synthetic rubber compounds that prevent oxygen molecules from leaking out. Surrounding this bladder is a high-tensile structural restraint layer designed to absorb the massive outward expansion force of the internal pressure. Outside of that sits a thermal insulation blanket composed of dozens of alternating layers of aluminized mylar and Dacron mesh, separated by vacuum gaps, which traps interior body and equipment heat like a massive thermos. However, moving underground creates its own set of critical engineering trade-offs: power distribution and access logistics. Living inside a lava tube means human settlers are permanently cut off from natural sunlight. Every watt of energy needed to light the living quarters, power life support systems, and run indoor agriculture must be generated on the surface and piped deep underground through heavy, high-voltage conduits. Furthermore, accessing the surface requires multi-stage airlock elevators installed through the volcanic skylights. Every time an astronaut or rover exits the underground lava tube to conduct surface operations, they must pass through an airlock system that undergoes a rigorous dust decontamination cycle. Dust management is the ultimate operational battle for any Martian habitat. Martian dust is not like soft beach sand on Earth. Because there is no liquid water or thick atmosphere to weather and round the soil particles over time, Martian regolith consists of microscopic, jagged mineral shards saturated with toxic perchlorate salts and iron oxides. When astronauts work on the surface, this fine dust acquires a strong electrostatic charge, causing it to cling aggressively to suit fabrics, visors, and mechanical joints. If astronauts step out of their suits inside the habitat, That abrasive dust falls onto the floor, becomes airborne in the ventilation system, and is inhaled by the crew, causing severe respiratory inflammation while grinding away at internal mechanical seals. To solve this, modern base architectures utilize a concept known as a suit port. Instead of bringing spacesuits inside an airlock, the suits remain permanently mounted to the outside of the habitat wall. The spacesuit features a rear entry hatch that seals directly against a matching hatch on the outer wall of the base. To go on a surface walk, the astronaut slides feet first through the wall hatch into the back of the suit, seals the inner door, and detaches from the habitat wall. The dirty exterior of the suit never enters the living space, and the clean interior air of the base is never exposed to the toxic surface dust outside. This simple mechanical isolation eliminates the need for massive airlock depressurization pumps while keeping the interior air pristine. To support long-term expansion beyond the initial inflatable modules, a growing base must eventually transition to local manufacturing using 3D printed regolith concrete. Autonomous robotic landers, equipped with microwave sintering heads or solar concentrators, collect the raw surface soil, heating it to over 1,100 degrees Celsius to melt the basaltic glass inside. As the melted soil cools, it fuses into dense, rock-hard structural blocks, retaining its strength without needing water or imported binding agents. 3D printing rovers can layer this molten regolith over surface habitats, forming thick protective shells, blast walls around rocket landing pads, and reinforced roads. By combining the natural shield of subterranean lava tubes with 3D printed regolith structures on the surface, humanity creates its first permanent, multi-layered fortress on another world. As the heavy structural seals lock into place, the airlocks equalize, and the environmental control systems pressurize the living modules. The raw mechanical shell of the base stands complete. The structure is anchored. The high-strength aramid walls hold the interior pressure stable against the thin vacuum outside, and the thick volcanic rock overhead blocks the silent drizzle of cosmic rays. Yet, as the crew steps inside the quiet, newly inflated habitat, they face an immediate life or death reality. The rooms are filled with inert nitrogen gas brought from Earth, and the biological clock on their finite reserve tanks is running out. To take their first unassisted breath inside this new home, the settlers must turn on the base's primary chemical engine, a machine that must continuously process the poisonous frozen air of Mars to extract the one element human life cannot exist without for more than 3 minutes: pure, breathable oxygen, producing oxygen. What if the most critical chemical reaction in human history isn't one that creates energy to power our machines, but one that strips oxygen out of a poisonous, freezing atmosphere to keep our lungs from collapsing? When you step inside a freshly pressurized habitat on Mars, the ambient air is useless. The atmosphere outside is roughly 95% carbon dioxide, less than 3% nitrogen, and carries only trace amounts of free oxygen, less than 13%. On Earth, human lungs require a continuous supply of oxygen at a partial pressure of roughly 21 kilopascals to keep our blood saturated. If a human attempts to breathe the raw air of Mars, the immense concentration of carbon dioxide causes instant hypercapnia, overwhelming the bloodstream, rendering the person unconscious within seconds, and causing brain death shortly after. To make Mars livable, a colony must construct a chemical extraction grid that operates continuously every second of every day for decades without failing. There are no trees, no oceans filled with photosynthetic plankton, and no atmospheric reserves waiting to be tapped. Every single breath taken by a Martian settler must be manufactured through high-temperature industrial chemistry. This brings us to the fundamental engineering challenge of off-world life support: closed-loop recycling versus atmospheric harvesting. On the International Space Station, oxygen is produced using an advanced water electrolysis system. Electricity splits liquid water brought from Earth into hydrogen gas and oxygen gas. The oxygen is pumped directly into the cabin, while the hydrogen is combined with exhaled carbon dioxide inside a Sabatier reactor to recover water, which is then recycled back into the electrolysis loop. While this system achieves an impressive water recovery efficiency of over 98%, it carries a fatal vulnerability for a permanent Martian colony. It relies on a closed loop that slowly leaks. Every time an airlock opens, every time a suit seal wears out, and every time waste is ejected, water and gas escape into the vacuum. Over years, those small leaks add up to a massive mass deficit. To achieve true independence, Mars cannot rely solely on recycling recycled water. It must harvest fresh oxygen directly from the planetary atmosphere itself. The primary technology for atmospheric oxygen production on Mars is solid oxide electrolysis, or SOx-E. The chemistry behind solid oxide electrolysis is deceptively simple, but the engineering execution is extraordinarily harsh. The Martian atmosphere acts as an endless reservoir of carbon dioxide, text CO-tolysis. A carbon dioxide molecule consists of one central carbon atom bound tightly to two oxygen atoms by strong double covalent bonds. To break those bonds and liberate free oxygen molecules toppling tollers, text doubling tollers, you must force the gas through an extreme thermal and electrochemical process. Text 2CO2, right arrow text 2CO2, plus text 0009, plus of 2, plus of 2, right arrow text, plus 2CO2. First, an intake pump draws raw, dusty Martian air into the processing facility. Before the air can enter the chemical reactor, it must pass through multi-stage mechanical filters to remove the fine, abrasive regolith particles. If even a tiny fraction of microscopic dust bypasses these filters, the iron and perchlorate minerals inside the dust will coat the reactor membranes, causing immediate thermal hotspots and chemical poisoning of the catalyst. Once filtered, the carbon dioxide gas is compressed from the ambient Martian pressure of 7 millibars up to roughly 1 bar. This compression requires heavy mechanical compressors that must run continuously, facing intense mechanical wear from thermal friction. The compressed gas is then piped into the core of the solid oxide electrolysis unit, where it is heated to an astonishing 800 degrees Celsius. At 800 degrees Celsius, the thermal energy begins to vibrate the carbon dioxide molecules, weakening their molecular bonds. The superheated gas is then forced over a specialized ceramic membrane, typically made of yttria stabilized zirconia, a high-tech ceramic material coated with porous catalytic electrodes made of platinum or lanthanum compounds. When a high-voltage electrical current is applied across the ceramic membrane, a remarkable electrochemical separation occurs. The ceramic material acts as a solid electrolyte that allows only oxygen ions to pass through its crystal lattice. As the superheated carbon dioxide sweeps over the negative electrode, the molecules lose oxygen atoms, which absorb electrons to become oxygen ions. These ions are drawn directly through the solid ceramic wall to the positive electrode side. On the other side of the membrane, the oxygen ions give up their extra electrons, recombining to form pure molecular oxygen gas, E dollars text, or sign. The remaining byproduct on the inlet side, toxic carbon monoxide gas, text COE, mixed with unreacted carbon dioxide, is safely vented back into the Martian atmosphere or captured for industrial metal refining. Real space hardware has already proven that this exact chemical process works on the surface of Mars. In April 2021, NASA's Perseverance rover successfully deployed the MOXIE instrument. the Mars Oxygen In Situ Resource Utilization Experiment. Tucked inside the belly of the rover, MOXIE, a device the size of a car battery, drew in raw Martian air, compressed it, heated it to 800 degrees Celsius, and produced roughly 6 grams of pure oxygen per hour, enough to keep a small dog alive. Over its multi-year testing phase, MOXIE operated across different seasons, day and night, during dust storms and freezing conditions, proving that solid oxide electrolysis is a fundamentally sound technology for off-world survival. However, scaling a technology from a tiny 6 gram per hour experimental unit aboard a robotic rover up to an industrial plant capable of sustaining a human city introduces terrifying engineering trade-offs. Consider the human math. A single adult human consumes roughly 84 kilograms of oxygen per day just to stay alive. A small founding crew of 50 settlers will require over 42 kilograms of pure oxygen every single day purely for biological respiration. Far more daunting, however, is the propellant requirement. A return rocket taking that same crew back to Earth does not burn pure methane. It burns a propellant mixture that is roughly 78% liquid oxygen by mass. To launch a heavy return vessel off Mars, engineers must manufacture and cryogenically store over 250 tons of liquid oxygen. The oxygen required to breathe is a tiny drop in the bucket compared to the massive ocean of oxygen needed to fuel the rockets. To meet this demand, an industrial Martian oxygen factory must process thousands of cubic meters of atmosphere every hour. And this creates a severe operational trade-off: energy consumption versus thermal fatigue. Running a solid oxide electrolysis grid at 800 degrees Celsius requires massive amounts of continuous electrical power. Heating the ceramic membranes and running the mechanical compressors demands megawatts of energy, which must be supplied reliably by surface nuclear reactors or massive solar arrays. Furthermore, ceramic materials are notoriously brittle. When you heat yttria-stabilized zirconia up to 800 degrees Celsius, it expands significantly. If the power grid experiences a sudden fluctuation or blackout, the ceramic membranes cool rapidly, contracting unevenly. This thermal shock causes microscopic cracks to propagate through the delicate ceramic walls. Once a membrane cracks, high-pressure carbon dioxide leaks directly into the pure oxygen stream, contaminating the life support supply with lethal carbon monoxide. To prevent thermal shock failure, an oxygen factory can almost never be turned off. It must be maintained at a continuous 800-degree operating temperature for its entire operational lifetime, year after year, demanding flawless power grid stability and heavy redundancy across every heating element and control sensor. Even if the solid oxide electrolysis plant operates perfectly, producing pure gaseous oxygen is only half the battle. You cannot store tons of gas in room temperature tanks without requiring impossibly thick, heavy steel walls to hold the pressure. The gas must be converted into a liquid. Liquefying oxygen requires a massive cryogenic refrigeration infrastructure. Pure oxygen gas must be compressed and cooled down to minus 133 degrees Celsius, where it condenses into a pale blue, extremely dense liquid. Cryogenic liquid oxygen introduces its own extreme physical hazard, catastrophic material combustion. Pure liquid oxygen is a violent oxidizer. At high concentrations, materials that are normally non-flammable on Earth, including structural steel, rubber seals, synthetic lubricants, and titanium, can spontaneously ignite and burn furiously upon contact with a single spark or static discharge. A tiny microscopic speck of oil or grease left inside a high-pressure oxygen valve during assembly will detonate like a high explosive when exposed to liquid oxygen. Every pipe, valve, tank, and sensor inside the oxygen liquefaction plant must be manufactured under clean room conditions to be completely grease-free and non-sparking, using specialized nickel-copper alloys like Monel that resist oxygen fires. A single maintenance mistake by a technician servicing an oxygen line could instantly vaporize a section of the industrial processing facility. To ensure the survival of the base, oxygen production must be decentralized. A colony cannot rely on a single massive central factory. A localized explosion, a thermal shock crack, or a dust-clogged intake pump would place the entire population on a lethal countdown as habitat reserves drain. Instead, a resilient Martian base utilizes a modular grid architecture, multiple independent oxygen generation plants, each housing its own filtration pumps, ceramic electrolysis stacks, and cryo-coolers are stationed in isolated vaults around the perimeter of the base. These modules feed into a shared underground buffer network connected to high-pressure storage spheres and subterranean cryogenic tanks. If one plant suffers a ceramic fracture or a mechanical compressor failure, intelligent monitoring systems instantly isolate the damaged module, allowing the remaining grid to adjust output while automated repair units replace the damaged ceramic stacks. As the heavy compressors hum, the ceramic membranes glow red at 800 degrees inside their insulated vacuum jackets, and a steady stream of pale blue liquid oxygen trickles into the subterranean storage tanks. The immediate threat of suffocation begins to recede. The base now has air to fill its inflatable quarters and life support loops. Yet, as the engineers monitor the steady flow of fresh oxygen, they're confronted with a stark chemical limit. Humans cannot live on pure oxygen alone at normal atmospheric pressure. Breathing pure oxygen over long periods causes severe pulmonary oxygen toxicity, causing fluid buildup in the lungs and central nervous system damage. The habitat air must be diluted with a stable, inert buffer gas like nitrogen or argon to match Earth's atmospheric composition. And far more critically, oxygen provides only one component of the survival equation. Human biology, agricultural crops, and fuel production factories demand another fluid in massive quantities. A resource that cannot be extracted from the thin air above, but must be mined directly from the frozen, toxic ground beneath their feet, liquid water. Finding water. What if the most valuable substance on Mars isn't gold or rare industrial metals, but the frozen, dirty ice buried beneath a layer of toxic soil? Without water, every life support loop, agricultural greenhouse, and rocket propellant factory on Mars grinds to an absolute halt. Oxygen production through electrolysis demands water. Synthesis of liquid methane for return rockets demands water. Human hydration, food growth, and thermal cooling loops demand water in massive, unrelenting quantities. A small, self-sustaining settlement of 50 people will require hundreds of thousands of liters of pure, liquid water every single year simply to maintain baseline operations. For decades, early space architecture assumed that water would have to be recycled continuously in a hyper-efficient, 100% closed loop. But in reality, no mechanical system is perfect. Valves leak microscopic amounts of vapor into the atmosphere. Life support filters absorb moisture that cannot be fully recovered. And industrial chemical processes consume hydrogen permanently. A colony that attempts to live entirely on recycled water will slowly bleed its reserves dry. To survive for the long term, Mars cannot just recycle its water. It must mine it. The primary engineering challenge of Martian water mining is location and chemical purity. Mars holds vast reserves of water ice. At the polar caps, ice sheets kilometers thick stretch across thousands of square kilometers. But the polar regions are an operational, nightmarish trap. They face months of total, pitch-black darkness during the winter, where temperatures drop below -105 degrees Celsius. Freezing atmospheric carbon dioxide directly onto the ground as dry ice. Operating heavy mining machinery in total dark under dry ice snowfall is an unnecessary structural gamble. Instead, water mining operations focus on the mid-latitudes, regions like Utopia Planitia and Arcadia Planitia. Here, orbital radar data from spacecraft like NASA's Mars Reconnaissance Orbiter has revealed vast subterranean glaciers buried just 1 to 3 meters beneath the dry surface regolith. These underground ice sheets are thousands of square kilometers in size and up to 100 meters thick, left behind by ancient climate cycles millions of years ago. However, extracting this buried ice introduces a brutal engineering trade-off: mechanical excavation versus thermal mining. The traditional approach to mining involves heavy machinery: excavators, bulldozers, and haul trucks that scrape away the topsoil, dig up frozen ice blocks, and transport them to a central melting facility. But on Mars, mechanical excavation faces immediate failure modes. Subterranean Martian ice is not soft snow. At temperatures of minus 60 degrees Celsius, it is frozen as hard as structural granite. Attempting to chop, drill, or dig through granite, hard ice wears down heavy steel drill bits within days. Furthermore, operating heavy diesel-style tracked vehicles in freezing temperatures demands massive amounts of energy, while the abrasive surface dust continuously clogs mechanical joints, strips gear lubricants, and destroys hydraulic seals. To eliminate moving parts and reduce wear, modern space architects favor a thermal mining architecture known as a Rodriguez well or Rodwell. Developed originally for military and scientific outposts in Antarctica, a Rodriguez well extracts water without ever digging a giant hole or hauling heavy ice blocks across the surface. The operation begins with a lightweight automated drilling rig. The rig drills a narrow vertical hole through the top 3 meters of dry regolith until it reaches the solid subterranean ice sheet below. Once the drill bit hits the ice, it is withdrawn, and a thermal probe assembly is lowered down into the borehole. The probe consists of a closed-loop heat exchanger connected to a surface power plant, typically a small nuclear fission reactor. High-temperature fluid is pumped down through insulated pipes into the ice layer. As the heat radiates outward, it melts the surrounding ice, creating a subterranean cavern filled with a pool of liquid water deep beneath the surface topsoil. A submerged pump then draws the liquid water up through insulated pipes to the surface processing plant. A fraction of the hot water is recycled back down into the pool to maintain the thermal melting process, while the rest is piped directly into storage. The soil above acts as a natural structural sealing and thermal insulator, preventing the liquid water pool from evaporating outward into the thin atmospheric vacuum. A Rodriguez well eliminates the need for massive excavation machinery, minimizes surface dust exposure, and runs continuously with almost no moving parts. But solving the extraction problem instantly exposes a far more insidious failure mode: chemical contamination. Subterranean Martian ice is not pure, pristine spring water. Over millions of years, atmospheric dust, cosmic rays, and volcanic fallout have saturated the ice with dissolved mineral salts. The most dangerous of these contaminants are perchlorates, specifically calcium, magnesium, and sodium perchlorates. Perchlorate salts dissolve readily in water, forming a toxic solution. In humans, perchlorates interfere directly with the thyroid gland, blocking iodine absorption, disrupting metabolic regulation, and causing severe neurological damage. In industrial fuel factories, perchlorates corrode high-pressure steel pipes, poison chemical catalysts, and contaminate the liquid oxygen fuel stream. Furthermore, the raw water pulled from a Rodwell contains heavy concentrations of fine, suspended silt microscopic basalt and iron oxide dust particles that do not settle easily. If raw, unrefined water is pumped into a habitat life support loop, or an electrolysis unit, the silt will instantly clog reverse osmosis membranes, while the perchlorates will poison every biological crop inside the agricultural greenhouses. Every liter of water extracted from the ground must pass through a multi-stage industrial decontamination grid before it ever enters a human body or a machine. The first stage of decontamination is physical clarification. The raw, warm water is pumped into large settling tanks, where flocculants, chemical agents that bind to fine dust particles, are injected into the liquid. The microscopic silt clumps together, forming heavy sediment that settles to the bottom of the tank, where automated scrapers purge the sludge. The clarified water then enters a high-pressure, multi-stage reverse osmosis grid. The water is forced through specialized, semi-permeable membranes at pressures exceeding 50 bars. The microscopic pores in the membranes allow water molecules to pass through while trapping larger dissolved perchlorate ions, heavy metals, and residual mineral salts. To ensure total chemical purity, the concentrated brine rejected by the reverse osmosis filters is piped into a secondary catalytic destruction unit. Here, the perchlorates are exposed to high heat and specialized titanium-ruthenium catalysts, breaking the toxic perchlorate ions down into harmless chloride salts and free oxygen gas. The water is boiled into steam inside sealed vacuum chambers, leaving behind any trace chemical impurities, and then condensed back into pure, medical-grade liquid water. Text: HER2 text $. This multi-stage decontamination process yields water pure enough for human consumption, hydroponic agriculture, and high-efficiency, solid oxide electrolysis. But running an industrial water extraction and purification grid creates an extreme operational trade-off: thermal energy management versus structural freezing. Water has an extraordinarily high specific heat capacity, meaning it requires immense amounts of thermal energy to melt ice and prevent liquid water from freezing. On Mars, where surface temperatures plunge to -80°C every night, any pipe carrying liquid water will freeze solid within minutes if the thermal heating system fails. When water freezes, it expands by roughly 9%. If a water pipe cools below 0°C, the ice expansion generates internal pressures of over 2,000 bars, enough to instantly burst high-strength steel or composite pipes, dumping thousands of liters of precious water onto the ground, where it instantly freezes into solid rock or sublimates away into the thin atmosphere. To prevent catastrophic thermal freezing, the entire water infrastructure, from the subterranean rod wells to the processing plants and habitat storage tanks, must be wrapped in multi-layered vacuum insulation jackets and continuously heated using waste thermal energy from the colony's central nuclear reactors. Every waterline features redundant heating elements, double-walled containment jackets, and automated emergency flush valves. If a power grid failure or thermal line rupture is detected, intelligent monitoring systems instantly inject pressurized nitrogen into the pipes, blowing all liquid water back into insulated subterranean holding tanks before it can freeze inside the conduits. As the nuclear heat flows deep into the buried glaciers, the underground Rodwell caverns stabilize, and a continuous stream of pure, crystal-clear water flows through the insulated processing grid into the colony's central reservoirs. The base now has breathable air, pressurized living modules inside natural volcanic rock, and a reliable flow of pure water. Yet, as the settlers celebrate this critical achievement, their focus turns to the dinner table. The pre-packaged meal rations brought from Earth are steadily shrinking, and the biological clock on their finite food supply is ticking down. To survive for years without starving, the colony must take its next, most complex biological step, transforming the toxic, sterile dirt of Mars into a thriving agricultural ecosystem that can feed a human population under an artificial sky. Growing food. What if the hardest biological challenge on Mars isn't keeping human beings alive, but forcing Earth's plants to grow in a toxic, sterile soil that has never seen a drop of organic life in 4 billion years. Every settlement in human history survived because it could feed itself from the land around it. A Mars colony that relies on supply ships from Earth for its daily calories is a colony living on borrowed time. Shipping pre-packaged freeze-dried meals across interplanetary space costs thousands of dollars per kilogram, and a single orbital conjunction delay or launch failure back on Earth would plunge the settlers into a catastrophic famine. To achieve permanent survival, the red planet must become a farm. However, turning Mars into an agricultural producer forces space botanists and agricultural engineers to confront a brutal reality. Martian dirt is not soil. On Earth, soil is a living, complex ecosystem composed of weathered rock, decomposed organic matter, water, and billions of microbial organisms like bacteria and fungi that break down minerals into bioavailable nutrients. Martian soil, known as regolith, is simply crushed volcanic basalt and iron oxide. It contains zero organic material, zero nitrogen-fixing bacteria, and zero natural biology. Worse still, the regolith is saturated with chemical toxins. Data from NASA's Phoenix lander, along with the Curiosity and Perseverance rovers, revealed that Martian regolith contains between 0.5 to 1% perchlorate salts by mass. Perchlorates are powerful oxidizing agents that act as a systemic plant poison. When plants absorb perchlorates through their root systems, the chemical disrupts cellular water uptake, destroys chlorophyll production, and inhibits photosynthesis, causing the crops to wither and die within days. Even if a plant somehow managed to survive low perchlorate exposure, it would absorb the toxic chemical into its leaves, stems, and fruits. A human settler eating crops grown in raw Martian regolith would ingest dangerous levels of perchlorates, leading to severe thyroid shutdown, aplastic anemia, and bone marrow failure. This brings us to the core agricultural trade-off: regolith remediation versus closed-loop hydroponics. To utilize the vast quantities of regolith on Mars, the soil must undergo a rigorous chemical decontamination process. First, the raw regolith is washed with warm water extracted from subterranean Rodriguez wells. Because perchlorate salts are highly soluble, the water leaches the toxins out of the dirt. The contaminated wash water is then routed through catalytic destruction units to break the perchlorates down into harmless chlorides and oxygen. Once the toxins are removed, the sterile regolith must be biologically activated. Engineers must mix the washed regolith with composted human solid waste, properly heat sterilized to kill human pathogens, and inoculate the dirt with engineered strains of nitrogen-fixing bacteria like rhizobium and mycorrhizal fungi. Over months of careful biological management, this sterile volcanic sand transforms into living, fertile soil. While regolith remediation works for long-term expansion, early agricultural systems rely on a far more controlled, high-efficiency architecture: closed-loop aeroponics and hydroponics. Instead of growing crops in dirt, hydroponic systems suspend plant roots in nutrient-rich water solutions, while aeroponic systems suspend the roots in mid-air inside sealed dark chambers, spraying them with a fine aerosol mist of liquid nutrients every few minutes. Aeroponics consumes 95% less water and 90% less physical space than traditional earth farming, while delivering oxygen directly to the root zones, accelerating plant growth rates by up to 200%. However, shifting to high-tech indoor farming introduces a critical environmental trap: light and atmosphere management. Mars sits roughly 228 million kilometers from the Sun. At that distance, sunlight intensity on the surface is only 43% as strong as it is on Earth. Furthermore, because habitats must be buried under 2 meters of regolith or built inside subterranean lava tubes to protect against cosmic radiation, plants cannot receive natural sunlight. Every photon of light required for photosynthesis must be generated artificially using high-efficiency LED grow lights tuned precisely to the blue and red absorption spectrums of chlorophyll. Running thousands of square meters of high-intensity LED grow lights creates an immense power demand. A farm large enough to supply the caloric needs of 50 settlers requires nearly 200 kilowatts of continuous electrical power just for lighting, placing a massive burden on the colony's nuclear reactors. Beyond light, the atmospheric composition inside the agricultural domes requires precise chemical tuning. Plants thrive in high carbon dioxide environments. By raising the internal habitat, carbon dioxide levels to roughly 1,000 parts per million, nearly 3 times Earth's ambient level. Crops like potatoes, sweet potatoes, soybeans, and wheat grow at accelerated rates, producing massive yields in compressed timeframes. Yet, as the crops flourish under the artificial sky, a silent biological danger emerges: genetic stagnation and crop disease. In a closed, sealed environment, a single airborne plant pathogen, such as a fungal spore or bacterial blight, can spread through the ventilation ducts and water recycling loops, wiping out the entire food supply of the colony within a week. On Earth, farmers rely on natural wind, soil biodiversity, and chemical pesticides to manage outbreaks. On Mars, where air and water are continuously recycled back into the human living quarters, synthetic chemical pesticides cannot be used without poisoning the settlers. To prevent total agricultural failure, the farm architecture uses strict biological isolation. The agricultural grid is split into dozen independent sealed greenhouse vaults separated by airlocks and negative pressure isolation zones. Each vault operates its own isolated air filtration system and nutrient water loop. If a fungal blight or genetic mutation takes hold in Vault 3, intelligent sensor networks detect the drop in photosynthetic efficiency, instantly sealing the module and flushing the vault with concentrated ozone to sterilize the biological threat before it can reach the rest of the farm. Furthermore, crop selection is strictly optimized for caloric density, harvest index, and nutritional balance. Space botanists focus on crops where the majority of the plant is edible. Dwarf varieties of wheat, energy-dense potatoes, protein-rich soybeans, and nutrient-dense microgreens form the core of the Martian diet. The non-edible plant material, such as roots, stalks, and leaves, is not thrown away. It is routed into automated anaerobic digesters, where microbes break down the plant's cellulose, producing nutrient-rich compost for regolith farms and biogas for industrial heating. Every atom of carbon, nitrogen, phosphorus, and potassium is locked into an unforgiving, continuous recycling loop. The nitrogen exhaled in human waste feeds the plant roots. The plants produce oxygen and edible carbohydrates. The humans consume the crops, and the cycle repeats without end, living through dust storms. What if the most dangerous weather event on Mars isn't a freezing blizzard or a hurricane, but a silent, rising wall of fine dust that chokes off the sun for months, draining your power grid while grinding your machinery to a halt from the inside out? On Earth, dust storms are localized, temporary events lasting a few hours or days. On Mars, the atmospheric physics create a phenomenon unique in the solar system: global dust events. Every few Earth years, as Mars passes closest to the Sun during its southern summer, intense solar heating creates massive thermal updrafts in deep basins like Hellas Planitia. These updrafts suck microfine iron oxide dust high into the upper atmosphere, where high-speed winds carry it around the entire globe. Within days, individual local storms merge into a single, planet-encircling blanket of darkness that can linger uninterrupted for 3 to 6 months. For a human colony on Mars, a global dust storm is an operational nightmare that threatens every single life. support an industrial system on the base simultaneously. The first fundamental threat of a global dust storm is light attenuation. Martian dust particles are ridiculously tiny, averaging just 1 to 3 micrometers across, finer than talcum powder. Suspended high in the thin air, these microscopic particles absorb and scatter incoming sunlight. During the peak of a global dust event, atmospheric opacity, measured as Tor climbs from a normal baseline of 0.5 to over 5. 0. This means that up to 99% of direct sunlight is blocked from reaching the surface. The sky turns from its usual butterscotch hue into a dark, eerie reddish twilight at midday and total pitch black at night. For early robotic missions reliant on solar power, global dust storms were death sentences. In 2018, NASA's Opportunity rover, which had operated continuously on Mars for over 14 years, was engulfed by a global storm and endurance crater. As the dust blocked the sun, the rover's solar panels stopped generating power. Unable to keep its internal heaters running through the freezing nights, Opportunity's electronics froze, its clock failed, and the mission went permanently silent. A human colony cannot afford to go silent. If a dust storm cuts solar power generation by 95%, the base faces an immediate energy crisis. Without continuous power, the solid oxide electrolysis units stop producing oxygen. The Rodriguez wells freeze solid underground. The LED grow lights inside the agricultural vaults shut off, and the habitat's interior heaters fail, allowing room temperatures to drop toward minus 60 degrees Celsius within hours. This brings us to the core energy trade-off: solar reliance versus nuclear resilience. A colony that relies solely on solar panels and batteries must build massive redundant solar arrays spread across kilometers of land, combined with colossal battery storage systems to survive a multi-month blackout. But solar panels carry a fatal mechanical flaw during a dust storm: static dust accumulation. As the storm rages, fine, highly abrasive dust continuously settles out of the air, coating every horizontal surface in a blanket of rust-colored dirt. Even after the atmospheric storm clears months later, the solar arrays remain coated in dust, preventing them from recovering power generation. To overcome this, engineers have designed active dust-clearing mechanisms, such as electrostatic dust shields. By embedding ultra-thin, transparent electrode wires inside the glass covers of solar panels and applying high-voltage, low-current electrical pulses, the system generates a traveling electrostatic field that lifts and pushes the charged dust particles off the glass. But running electrostatic clearing fields continuously across vast solar farms consumes massive amounts of energy, the very energy the storm is draining from the colony. Because of this vulnerability, the permanent Martian base must decouple its survival grid from solar power entirely, anchoring its power infrastructure with nuclear fission reactors buried safely underground. Yet, even if the colony's nuclear reactors provide continuous, uninterrupted electricity throughout the months of darkness, the storm attacks from a second, far more insidious angle: mechanical abrasion and electrostatic infiltration. Martian dust is not soft, weathered dirt. Because there is no liquid water or thick atmosphere to smooth the sharp edges of rock fragments over eons, Martian dust consists of microscopic jagged shards of glass, basalt, and toxic perchlorate salts. Driven by surface winds reaching speeds of over 100 kilometers per hour, this microscopic dust acts like a relentless, low-pressure sandblaster. It scours reflective window coatings, erodes delicate optical lenses on surface navigation cameras, and wears away the protective sealants on airlocks and hatch mechanisms. Far worse than surface erosion is dust infiltration into moving parts. Because the dust particles are only a couple of micrometers wide, they penetrate standard mechanical joints, bearing housings, and sealed airlocks. On Earth, machines use liquid oil or grease to lubricate gears and bearings. On Mars, If you apply traditional grease to a gear joint exposed to dust, the fine iron oxide particles mix with the oil, creating a thick, highly abrasive grinding paste that destroys steel gear teeth within hours of operation. To survive the dust, Martian machinery must abandon liquid lubricants entirely, shifting to dry lubricants like molybdenum disulfide or tungsten disulfide, combined with magnetic fluid seals. A magnetic fluid seal uses a ferrofluid, a liquid containing suspended magnetic nanoparticles, held in place around a rotating shaft by strong permanent magnets. The magnetic field creates a liquid wall that blocks microscopic dust from entering the internal mechanical housing, while allowing the drive shaft to rotate smoothly without wearing out solid rubber gaskets. While mechanical systems battle abrasion, the storm introduces a bizarre atmospheric hazard: static electrical discharge. As billions of dry, iron-rich dust particles collide with one another in the high-speed winds, triboelectric charging occurs. The same friction process that creates static electricity when you rub a balloon against hair. The entire dust storm becomes a massive, low-density electrostatic field. While the thin Martian air cannot support massive, earth-shattering lightning strikes, the storm generates continuous, localized glow discharges and miniature static arcs across metal structures, communications antennas, and rocket landing pads. These static discharges create intense electromagnetic interference, scrambling unshielded radio communications between the base and surface rovers, while threatening to fry sensitive microelectronics inside external monitoring sensors. Every surface structure, radio mast, and power line must be heavily grounded through deep copper rods driven deep into the subterranean regolith, while external electronic circuits must be enclosed inside copper Faraday cages to block static electromagnetic pulses. For the human crew sealed inside the base, living through a global dust storm is a psychological and operational endurance test. Outdoors, the world has vanished into a dark, howling, reddish fog. Surface walks are cancelled, external maintenance operations are strictly prohibited, and the crew is confined to the subterranean lava tube quarters and inflatable modules for months on end. The habitat's environmental control systems run at maximum filtration capacity, continuously cycling the interior air through multi-stage, high-efficiency particulate air, HEPA filters, and electrostatic precipitators to trap any rogue dust particles that manage to bypass the airlocks. Inside the sealed agricultural vaults, the magenta LED lights burn brightly, powered by the steady hum of the underground nuclear reactors. The crops continue to grow, the solid oxide electrolysis units continue to crack oxygen out of compressed gas, and the purified glacial water flows quietly through the habitat loop. After 4 grueling months, the planetary winds begin to subside. The airborne dust slowly settles back onto the barren red plains, and the butterscotch sky begins to clear, allowing faint, pale sunlight to strike the surface once again. The colony has weathered the storm. Its mechanical seals held against the abrasive dust, its grounded Faraday cages protected its microelectronics, and its nuclear power grid kept its life support loops running without missing a single beat. Yet, as the settlers step back out onto the surface to inspect the dust-coated landscape, they realize a profound structural truth. To expand from a small, fragile outpost into a thriving, multi-generational city, they cannot keep relying on temporary emergency measures or small nuclear modules. They need an energy grid capable of generating gigawatts of continuous power. A massive industrial energy backbone that can power heavy manufacturing plants, heat entire subterranean cities, and drive the massive industrial machines needed to reshape an entire planet, powering an entire colony. What if the primary limit to human survival on Mars isn't air, water, or food, but the brutal, non-negotiable math of electrical power? Every single life support loop, industrial factory, and agricultural light array we have discussed relies on a continuous, massive supply of energy. Oxygen production through solid oxide. Electrolysis demands superheating carbon dioxide to 800 degrees Celsius. Water extraction through subterranean Rodriguez wells requires melting frozen glaciers buried under rock. Food production demands hundreds of kilowatts of continuous electrical light. The moment the power grid drops below a critical voltage, the oxygen plants freeze, the water pipes burst, the farm lights go dark, and the countdown to human extinction begins. To scale a base from a fragile science outpost of 10 astronauts into an industrial city of thousands, the colony's power grid must transition from kilowatts to gigawatts. This brings us to the ultimate energy trade-off: solar arrays, radioisotope generators, or nuclear fission grids. Early space missions relied heavily on radioisotope thermoelectric generators, or RTGs, like those aboard the Voyager probes, the Curiosity rover, and the Perseverance rover. RTGs generate electricity from the natural radioactive decay of plutonium-238. They are extraordinarily reliable, contain zero moving parts, and run continuously for decades, regardless of dust storms or distance from the sun. However, RTGs carry a fatal scaling limit: power density. A state-of-the-art space, RTG produces barely 100 to 200 watts of electrical power, roughly enough to run a single household light bulb, while requiring kilograms of rare, refined weapons-grade isotopes that cost millions of dollars to produce on Earth. You cannot power an oxygen factory or heat an underground city with an RTG. It is simply a trickle of electricity meant for low-power robotic sensors. Solar power, as we saw during global dust storms, carries severe operational vulnerabilities. Even during clear Martian weather, solar energy faces severe physical limits. Mars receives less than half the solar energy that Earth receives. To generate a single megawatt of continuous electrical power on Mars using solar panels, a colony must deploy and maintain hundreds of thousands of square meters of delicate photovoltaic glass, combined with massive chemical battery banks to store power through the 12-hour Martian night. Chemical batteries like lithium-ion introduce their own severe failure modes in cold environments. At -60 degrees Celsius, liquid battery electrolytes freeze, causing internal lithium plating, short circuits, and rapid capacity loss. Keeping a massive battery farm warm through the night consumes a huge fraction of the very energy the batteries were built to store. To build an energy grid that is truly immune to dust storms, night cycles, and freezing temperatures, a Martian colony must anchor its civilization on compact, high-efficiency nuclear fission reactors. The core technology for off-world nuclear power is the liquid metal-cooled or gas-cooled fast fission reactor, a direct evolution of NASA's kilopower technology. Unlike massive Earth-based nuclear power plants that require towering cooling towers and millions of liters of liquid water to operate, a space-rated nuclear reactor is remarkably compact. A 10-megawatt fission reactor core is no larger than a household trash can, fueled by highly enriched uranium-235 or plutonium-239 fuel rods encased inside high-strength refractory metal alloys like molybdenum or niobium. The physics of a space reactor are built around extreme simplicity and passive safety. Inside the reactor core, uranium atoms undergo controlled nuclear fission, splitting apart and releasing massive amounts of thermal energy. A liquid metal coolant, such as liquid sodium-potassium alloy or liquid bismuth, is pumped directly through the reactor core, absorbing heat and reaching operating temperatures above 900 degrees Celsius. This superheated liquid metal is then routed through a closed-loop heat exchanger connected to Stirling engines or closed-loop Brayton cycle turbines. The extreme thermal energy expands gas inside the turbines, spinning high-speed generators that convert heat directly into megawatts of electrical power. However, operating a multi-megawatt nuclear power plant on Mars introduces a terrifying thermal management paradox: heat rejection in a vacuum. On Earth, nuclear plants reject excess waste heat by dumping hot water into rivers or evaporating it through giant cooling towers into a dense atmosphere. Mars has no oceans, no rivers, and an atmosphere so thin that it acts almost like a vacuum flask. Air convection on Mars is practically non-existent. You cannot simply place a hot radiator outside and expect the thin air to blow the heat away. According to the laws of thermodynamics, any heat engine that converts thermal energy into electricity can only operate if it has a temperature differential, a hot source and a cold sink. If a nuclear reactor cannot continuously dump its waste heat into the environment, the entire system overheats, the liquid metal coolant boils, and the reactor core undergoes a catastrophic thermal meltdown. To reject excess waste heat in a near vacuum, the colony must rely entirely on radiative thermal heat rejection. The power plant is connected to massive arrays of high-temperature heat pipe radiators spread across the surface. These radiators are filled with liquid titanium or potassium working fluids. Heat from the reactor's cold loop vaporizes the fluid inside the heat pipes, carrying the thermal energy to the outer radiator panels, where the heat radiates directly into space as infrared light. Text PBC, epsilon sigma, text AB, text AB, text ABC. By the Stefan-Boltzmann law, the power radiated, text PBC, increases exponentially with the fourth power of absolute temperature. Text TBC. To keep the radiator arrays physically compact, the radiators must operate at scorching temperatures, glowing bright red in the dark Martian night as they beam waste heat harmlessly into the sky. Yet, dumping waste heat into space creates an ironic engineering waste. While the electrical turbines produce megawatts of power, up to 70% of the nuclear reactor's energy is lost as low-grade waste thermal heat. Instead of radiating all this waste heat into space, smart colony architects use a combined heat and power grid architecture. The superheated liquid loop leaving the power turbines is piped directly through insulated subterranean conduits into the colony's underground infrastructure. This waste heat is used to warm the frozen rock walls of subterranean lava tubes, heat the water inside the Rodriguez well cabins to melt subterranean glaciers, and maintain comfortable room temperatures inside human habitats without spending a single watt of electrical energy. The nuclear reactor becomes both the electrical power plant and the central heating furnace for the entire city. To ensure safety, reactor placement relies on natural geological shielding. A nuclear reactor core emits high fluxes of dangerous gamma radiation and fast neutrons that can damage microelectronics and kill human cells. Rather than building heavy lead and concrete shielding domes on the surface, autonomous construction rovers lower the reactor cores deep into natural volcanic shafts or drilled rim pits kilometers away from the human living quarters. Dozens of meters of solid basalt rock act as a natural radiation shield. High-voltage direct current, HVDC power cables, run underground from the distant reactor pits to the central distribution hubs beneath the city. However, placing nuclear reactors miles away creates a new failure mode: power grid line losses and single-point cascading blackouts. If a main power conduit breaks due to ground shifting, thermal stress, or a rover accident, an entire sector of the city loses power instantly. To prevent catastrophic failure, the colony utilizes a decentralized microgrid architecture. Instead of relying on one massive central nuclear plant, the city is powered by a ring of small, modular nuclear reactors, each producing 10 to 50 megawatts, placed at strategic intervals around the colony perimeter. All the reactors feed into a smart, self-healing power grid managed by redundant artificial intelligence networks. If Reactor 3 suffers a turbine pump failure or a radiator line rupture, intelligent circuit breakers isolate the damaged plant in milliseconds, while the remaining reactors instantly throttle up their power output, rerouting electricity through secondary underground power loops to keep the life support systems and oxygen plants running uninterrupted. With a ring of nuclear reactors humming quietly beneath the volcanic rock, generating continuous gigawatts of electrical power and pumping vast rivers of thermal heat through subterranean pipes, the colony breaks free from its energy limits. The base is no longer a fragile outpost counting every watt. It has the energy required to melt underground glaciers, at industrial scales, run high-temperature oxygen factories 24 hours a day, and light vast indoor agricultural forests beneath the dirt. With unlimited energy flowing through the grid, the settlers turn their attention to the final barrier preventing them from expanding across the planet: physical space. They can no longer live inside flexible plastic inflatable modules shipped from Earth. To house thousands of engineers, scientists, botanists, and children, they must learn how to take the raw red dirt of Mars and transform it into towering structural cities built to last for centuries, expanding into a city. What if the ultimate test of a multi-planetary civilization isn't building a rocket to leave Earth, but turning the raw dirt of another planet into a home that can stand for 1,000 years? To transition from a science outpost into a true, self-sustaining city, human architecture on Mars must break its dependency on Earth manufacturing. You cannot ship steel girders, concrete mixers, or massive glass panels across millions of kilometers of deep space. Importing structural building materials from Earth costs upwards of tens of thousands of dollars per kilogram. An economic impossibility for an expanding city housing thousands of citizens. If a city is to grow, it must be constructed entirely out of what is already there: the red dust, basaltic rock, and thin air of Mars. However, building a permanent city on Mars forces civil engineers to face a brutal material reality. Traditional Earth-based construction methods fail instantly in the Martian environment. On Earth, standard concrete is made by mixing Portland cement, water, sand, and gravel. On Mars, using liquid water to mix concrete is an unacceptable waste of a precious, life-critical resource. Furthermore, standard concrete requires weeks to cure under atmospheric pressure and warm temperatures. In the near-vacuum, sub-zero environment of Mars, the water inside liquid concrete would freeze instantly or evaporate outward, leaving behind a brittle, crumbling structure filled with microscopic air pockets. Steel framing presents a similar failure mode. Refining raw iron ore into structural steel requires massive blast furnaces, vast quantities of carbon, and industrial processing grids that take generations to build. To construct a city without water or steel, space architects turn to advanced additive manufacturing, 3D printed regolith, concrete, and microwave sintering. Martian regolith is rich in basaltic minerals, silicon, iron, aluminum, magnesium, and calcium oxides. Basalt is an extraordinary structural material. When melted and cooled, it forms a dense, glass crystalline rock with a compressive strength significantly higher than standard Earth concrete. The primary construction tool for a Martian city is the autonomous 3D printing rover. Before human builders even step onto a site, swarms of heavy autonomous rovers are deployed across flat basaltic plains. These rovers collect raw surface regolith, running it through magnetic separators to extract iron and heavy basaltic minerals. The refined dust is then fed into high-power 3D printing heads, equipped with microwave magnetrons or focused solar concentrators. Microwave sintering works through a process called dielectric heating. Basaltic dust contains iron oxides that absorb microwave radiation at specific frequencies. When the 3D printer blasts the regolith with intense microwave energy, the dust particles heat to over 1,100 degrees Celsius in seconds, melting the outer edges of the mineral grains. As the rover moves along a programmed trajectory, the melted basalt fuses into a continuous, rock-hard structural layer. By depositing layer upon layer of molten regolith, autonomous 3D printers can construct thick structural walls, vaulted arches, blast shields around rocket pads, and paved roads without using a single drop of liquid water. However, printing a building on Mars introduces a radical structural challenge: tensile stress versus compressive load. Basalt concrete is exceptionally strong under compression, meaning it can support immense weight pushing down on it. But it is notoriously weak under tension, meaning it cracks easily when pulled apart from the inside. As we saw in early base design, the interior of a Martian habitat must be pressurized to roughly 1 bar so humans can live without suits. This creates an intense outward pushing force of 10 tons per square meter on every wall. A surface-printed 3D building is under constant, violent tension, trying to explode outward into the thin vacuum. To solve this tension paradox, architects utilize a dual-layer catenary arch design combined with regolith overburden. Instead of printing flat walls or square rooms, which create extreme stress points at the corners, 3D printers build catenary domes and parabolic vaults. A catenary curve distributes internal pressure evenly across the entire structure, eliminating high-stress corners. Furthermore, once the catenary dome is printed, heavy excavators heap a 2 to 3 meter thick layer of loose regolith over the top of the structure. The massive downward weight of this heavy dirt layer exerts a compressive force that directly counteracts the outward tensile push of the internal air pressure. The building achieves structural equilibrium, held together by a precise balance between the air pushing out and the dirt pushing down. While surface catenary domes provide large open spaces, a growing city must expand its underground footprint to connect hundreds of buildings into a unified urban network. Walking outside in a heavy spacesuit every time a citizen wants to go to work, visit a farm, or meet another person is an operational bottleneck. Every airlock cycle wears out mechanical suit joints, wastes small amounts of atmospheric gas, and risks tracking toxic perchlorate dust inside. To eliminate suits for daily city life, the colony builds an interconnected subterranean network using automated tunnel boring machines, or TBMs. Powered by the city's underground nuclear power grid, electric tunnel boring machines melt and grind their way through the solid basalt bedrock beneath the surface. As the cutting head grinds forward, heat elements melt the interior rock walls, creating a smooth, glassy basalt liner that seals the tunnel against gas leaks. These underground tunnels, spanning kilometers beneath the red desert, link residential catenary domes with industrial manufacturing zones, agricultural vaults, and nuclear power hubs. Pressurized electric transit cars glide through these subterranean arteries, allowing thousands of citizens to travel across the entire city in shirt-sleeve comfort without ever seeing the sky or putting on a pressure suit. As the city expands underground, its interior architecture transforms to support human psychological well-being. Living under meters of dirt or deep inside volcanic rock for years can induce severe sensory deprivation, claustrophobia, and seasonal affective disorder. Human biology evolved under open blue skies, natural sunlight, and green landscapes. To keep a multi-thousand-person population mentally healthy, interior architects design massive central plazas called biodomes within giant reinforced lava tube junctions. These subterranean caverns spanning hundreds of meters across and dozens of meters high, are lit by massive overhead LED skylights tuned to replicate the natural Rayleigh scattering of Earth's atmosphere. The air is enriched with oxygen from the agricultural farms, and the floors are terraced with living green parks, flowing water channels fed by purified glacial water, and trees grown in remediated regolith. These biodomes act as the social and biological heart of the city. A place where citizens can gather under an artificial sky, breathe fresh forest-scented air, and experience an ecosystem that mirrors the world their ancestors left behind. Yet, building a city for thousands of people introduces a terrifying new vulnerability: life support cascade failure. In a small outpost of 10 people, environmental control systems are simple and localized. In a city of 10,000 people, the metabolic load is immense. The population produces tons of carbon dioxide, liquid waste, and organic material every single hour. A failure in the central atmospheric scrubbing grid or a chemical contamination in the main water supply could poison an entire sector of the city within a day. To prevent catastrophic urban collapse, the city abandons centralized life support in favor of a cellular, decentralized environmental grid. The city is partitioned into self-contained atmospheric and hydrological districts. Each catenary dome and underground sector operates its own independent solid oxide electrolysis units, water recycling loops, and air scrubbing systems. High-speed automated blast doors stand ready at every tunnel junction. If a structural failure occurs in Sector 4, such as an uncontained pressure leak or a major fire-intelligent monitoring systems, drop the blast doors within milliseconds, isolating Sector 4 from the rest of the city. The remaining districts automatically rebalance their environmental controls, preventing the pressure loss or toxic gas from cascading through the subterranean tunnel network. With 3D printed regolith domes dotting the surface, electric transit cars humming through glassy basalt tunnels, and vibrant green biodomes glowing brightly deep underground, the physical shell of the first off-world city stands secure. It is a city built without steel or water brought from Earth. A city forged entirely out of the red dirt, nuclear energy, and human ingenuity. Yet, as the engineers celebrate the completion of this monumental urban network, a new, profound milestone approaches. Among the doctors, engineers, and scientists living inside these pressurized vaults, the first children are about to be born. A new generation of human beings who will take their very first breath on Mars, never knowing the feel of Earth's heavy gravity, its blue sky, or its open oceans, raising the first generation born on Mars. What if the most profound transformation in human history isn't building machines that can survive on another world, but watching human biology itself change to adapt to a planet it was never designed for? For decades, every human being who walked on Mars was an immigrant, a visitor born on Earth, whose bones, heart, lungs, and DNA were forged under the heavy pull of one standard Earth gravity. Their bodies were evolutionary products of 4 billion years of terrestrial biology. But a city cannot remain a permanent colony if its population must be continuously imported from across the solar system. For Mars to become a true home, humans must reproduce there. And the moment a child is conceived, carried to term, and born inside a pressurized Martian city, humanity splits into 2 distinct biological branches. The fundamental biological challenge of raising a human generation on Mars is partial gravity. Mars operates at 0.38 g, roughly 38% of Earth's surface gravity, while 7.38 g is enough to allow fluid mechanics to function and keep furniture anchored to the floor. It introduces a terrifying biological question that medical science has never been able to answer on Earth. Can a human fetus develop normally in partial gravity? On Earth, gravity acts as a constant physical blueprint during embryonic development. From the moment a fertilized egg begins to divide, gravity dictates spatial orientation, cell migration, and tissue organization. In microgravity aboard the International Space Station, animal studies revealed severe developmental abnormalities. Cells failed to signal correctly, embryonic division lost structural symmetry, and vestibular systems inside the inner ear formed without proper orientation. In 38% gravity, the biological outcome is a complex medical frontier. During gestative development, the human fetus experiences significantly less physical resistance. As the child grows inside the womb, the lower gravitational load alters bone mineral deposition. On Earth, a developing skeleton requires physical resistance to signal osteoblasts, the cells responsible for building dense bone matrix to lay down calcium and phosphorus. A child developing in 038G builds a skeleton calibrated specifically for 038G. Their long bones, the femur, tibia, and humerus, grow longer, thinner, and significantly less dense than those of an Earth-born child. Their ribs and spinal column expand with less physical compression, resulting in a taller, lighter, and more slender physical stature. This anatomical adaptation extends directly to the cardiovascular system. On Earth, the human heart is a powerful muscular pump engineered to fight gravity every second of your life, forcing heavy blood upward from your feet to your brain. On Mars, the heart does not need to work nearly as hard. For a child born on Mars, the left ventricle of the heart, the chamber responsible for pumping oxygenated blood through the body, does not develop the thick muscular walls typical of an Earth-born human. The vascular system adapts to lower hydrostatic pressure. Their resting blood pressure is lower, their blood vessel walls are thinner, and their total blood volume is reduced. This biological adaptation creates an irreversible, one-way physiological trap. An Earth-born astronaut can train, exercise, and eventually return to Earth's heavy gravity, using intense physical therapy to rebuild degraded muscle and bone. But a child born on Mars, whose skeleton was constructed from day one in 038G, and whose heart was built to pump blood in partial gravity, can never visit Earth. If a native Martian adult steps onto Earth, the heavy in-gravity well will feel 3 times heavier than anything their body has ever experienced. Their low-density bones would crack under their own body weight, their thin blood vessels would struggle to push blood to the brain, and their heart would face immediate cardiovascular collapse. Earth, the ancestral homeland of their parents, is, to a native Martian, a lethal high-gravity death world. Yet, lower gravity and skeletal changes are only the visible biological adaptations. The far more insidious threat comes from the cellular level: developmental radiation exposure. As we have seen, a Martian city is shielded under meters of regolith or buried inside volcanic rock. But no shield is 100% impenetrable. A small, persistent fraction of background galactic cosmic radiation and secondary neutrons leaks into the city's living spaces. For an adult human whose cells have finished dividing, minor radiation exposure elevates long-term cancer risks over decades. But for an embryo, infant, or growing child, whose stem cells are dividing at exponential rates, even low-level cosmic radiation represents a severe developmental hazard. A single high-energy ion nucleus passing through a developing fetal brain can disrupt neural migration pathways, leading to permanent neurological deficits, cognitive impairment, or cellular mutations. To protect the first generation of native Martians, the city's urban architecture incorporates deep biological vaults known as maternity sanctuaries. Located in the deepest, most heavily shielded subterranean sectors of the city, under dozens of meters of solid basalt bedrock. These sanctuaries are wrapped in thick liquid water shields and heavy polyethylene insulation. Expectant mothers and young children spend the majority of their time inside these deep vaults, reducing their cumulative radiation exposure to levels lower than the natural background radiation on Earth's surface. While radiation is managed through physical shielding, the psychological and sensory development of a Martian child introduces a unique sociological challenge. A child born on Mars grows up inside an artificial, engineered environment. Their world consists of catenary, regolith domes, glowing magenta agricultural vaults, subterranean transit tunnels, and pressurized biodomes. They have never felt natural wind on their face without a suit, never smelled real rain falling on wild soil, and never looked up at an open blue sky without a thick layer of transparent radiation shielding glass above them. To a native Martian child, the concept of an open sky is a terrifying abstract idea. On Earth, infants look up and see infinite blue space. On Mars, looking through a surface window reveals a pale butterscotch sky, a small distant sun, and a barren red desert where stepping outside without a suit means instant death. This creates a distinct psychological worldview. Native Martians develop an acute, instinctual reverence for mechanical systems, atmospheric pressure readouts, and life support stability. They do not view technology as a luxury or a tool. They view it as an extension of their own biological lungs. Their language, culture, and social values evolve around resource conservation, absolute community cooperation, and engineering discipline. To a Martian child, wasting a liter of water or damaging an airlock seal isn't a simple mistake. It is a moral crime against the survival of the city. By the time the first generation of native Martians reaches adulthood, they stand a head taller than their Earth-born parents. They walk with a fluid, low-gravity stride, moving effortlessly across the catenary plazas of their subterranean home. When they look at their Earth-born parents, they see visitors from a heavy, distant ocean world. People who dream of blue skies, green forests, and open seas. When native Martians look up at the ceiling of the giant biodome, they do not see a prison or an outpost. They see their home. They have no memory of Earth, no biological attachment to its heavy gravity, and no desire to return to a planet they never knew. As these native Martians assume control of the city's nuclear power grids, oxygen plants, and 3D printing rovers, the strategic direction of the colony undergoes a radical shift. They are no longer content with simply surviving inside pressurized underground bubbles. They possess the energy, the industrial capacity, and the multi-generational lifespan needed to stop hiding from the harsh environment outside. Led by a new species of humans born under a red sky, the city prepares to launch the greatest engineering project in the history of conscious life, stepping out of the subterranean vaults to reshape the atmosphere, oceans, and temperature of an entire planet. The future of a multi-planet civilization. What if the ultimate goal of space exploration isn't building a permanent sanctuary to hide from a dead planet, but forcing that dead planet to come alive? For hundreds of years, human survival on Mars depended on containment. Humans lived behind thick regolith shields, inside sealed lava tubes, and under artificial lighting grids. Every breath of air was manufactured, every drop of water was filtered from subterranean ice, and stepping outside meant encasing the body in a pressurized suit. But a civilization cannot remain trapped inside pressure vessels forever. To achieve absolute planetary freedom, the native generations of Mars launched the largest, longest engineering endeavor in human history: terraforming. The systematic transformation of an entire planet's atmosphere, climate, and biological surface. The core physics of terraforming Mars comes down to a single thermodynamic goal: warming the planet to thicken its atmosphere. Mars is locked in a cold, low-pressure state because its atmosphere is too thin to retain solar heat. The current surface pressure averages around 7 millibars. To allow liquid water to flow freely across the surface without instantly evaporating into a vacuum, the atmospheric pressure must be raised above the Armstrong limit, past 60 millibars, toward a target of 300 to 500 millibars. To trigger a runaway greenhouse effect, engineers do not rely on slow, local processes. They deploy mega engineering architectures operating on a planetary scale. The first phase of terraforming begins in space: orbital mirror arrays. Constellations of ultra-thin, highly reflective solar sails spanning hundreds of kilometers across, made of engineered graphene and dielectric films, are positioned in stationary orbits high above the Martian poles. These orbital mirrors act as giant lenses, focusing incoming sunlight directly onto the polar ice caps. As the concentrated solar radiation strikes the poles, the temperature rises. The polar caps, composed of millions of cubic kilometers of frozen carbon dioxide dry ice, begin to sublimated, turning directly from solid ice into massive plumes of gas. Billions of tons of carbon dioxide gas are released directly into the thin air. Because carbon dioxide is a potent greenhouse gas, the released atmosphere traps more solar heat, which further warms the planet, melting more polar ice. This feedback loop initiates a self-sustaining planetary greenhouse cascade. To accelerate this atmospheric thickening, surface industrial complexes unleash super greenhouse gases. Colossal automated factories built across the equatorial plains draw local fluorine and sulfur from the regolith, synthesizing artificial halocarbons, specifically sulfur hexafluoride and specialized perfluorocarbons. These gases are thousands of times more effective at trapping heat than carbon dioxide. Releasing small concentrations of halocarbons into the atmosphere accelerates the thermal runaway, raising global temperatures by several degrees per decade. As global temperatures rise past the freezing point at the equator, a miraculous geological transformation unfolds. Liquid water returns to Mars. Subterranean glaciers, buried for 4 billion years, begin to melt. Streams of liquid water cut through the ancient dry riverbeds of Valles Marineris and Crisi Planitia. Lakes form in deep impact craters, and eventually, a shallow northern ocean. The Oceanus Borealis fills the vast northern lowlands. For the first time in human history, rain falls from a Martian cloud. With liquid water flowing and atmospheric pressure rising past 200 millibars, human settlers can step onto the surface without heavy pressure suits. They still require oxygen masks to breathe, but they no longer need pressurized suits to prevent their blood from boiling. They walk across the red dirt in insulated cold weather gear, under a sky that is slowly shifting from a pale butterscotch hue toward a deep, dusty purple. However, a thick atmosphere and liquid oceans are useless if the sun continuously strips them away into space. As we saw, Mars lost its atmosphere over billions of years because it lacked an internal magnetic field. To protect the newly created atmosphere from being eroded by the solar wind, humanity builds an artificial magnetosphere. A massive magnetic shield station is positioned at the Sun. Mars L1 Lagrange point, a gravitational equilibrium point between Mars and the Sun. Operating high-power superconducting magnetic coils, the station generates a continuous 1 to 2 Tesla magnetic dipole field. This artificial magnetic shield creates an invisible protective umbrella in space, deflecting the solar wind around Mars, preventing atmospheric stripping, and creating a safe magnetic haven for the entire planet below. With the atmosphere secured and water flowing, the final, most patient phase of terraforming begins: biological seeding. genetically engineered extremophile cyanobacteria, lichen, and Antarctic mosses are spread across the damp basalt plains. These primitive organisms absorb carbon dioxide, break down toxic perchlorate salts in the soil, and release a steady, continuous stream of oxygen through photosynthesis over centuries. It is a process that takes generations. A quiet, patient transformation carried out by billions of native Martians who know they will never live to see the final result. Centuries after the first small starship touched down in the red dust, the transformation is complete. The red planet is red no longer. From deep space, Mars shines as a vibrant world of blue oceans, green terraformed valleys, and white swirling clouds. The ancient volcanic lava tubes and 3D printed catenary domes still stand, preserved as historical monuments to the early pioneers who fought against entropy in the dark. Humans walk along the shores of the Northern Ocean under an open sky, breathing air forged by generations of biological management. Their children run across green hills in 38% gravity, leaping in long, graceful strides under a pale blue sunset. Humanity is no longer a single planet species fragile to a single asteroid impact, nuclear war, or planetary catastrophe on Earth. The human story is scattered across multiple worlds, anchored by two vibrant civilizations sharing a single solar system. The long fight against the unforgiving laws of physics has been won. Metal, fuel, and human ingenuity held together against the cold void of space, proving that life is not a temporary accident confined to a single world, but an unstoppable force capable of bringing dead planets to life. The lights of Mars shine brightly into the cosmic dark, secure in the knowledge that the human journey has only just begun. Good night.